Hi everyone, how are you today? First, let me apologize for my absence last week. I kind of gave you a little bit of a previous warning in the beginning of the semester that happened eventually. So I had to rush my dad into the emergency room last Friday. So yeah, it was quite a hassle. So that's why I had to cancel the class last minute even. Uh, for making up that class, basically as I said, I'm going to prepare the pre-recorded lecture recording, and then put up into the YouTube so that you can have an access. But one thing is, I'm not going to put that makeup lecture before the first midterm. I mean, we have only one midterm. There is no such thing like first or second midterm. Uh, scared you? Just a minute. No, sorry. So just in that, I don't want to put any extra burden just before the midterm exam that I had to study for this damn thing. Just like the midterm is like around corner. That's not what I'm going to do. So probably what I'm going to do is put that makeup lecture recording during the exam week, so that that's you don't have to worry about that extra thing. But once you get to finish all your exam during the mid week, then you can digest. You can study for that missed part. So bottom line is that makeup lecture portion is not going to be part of the upcoming midterm exam at least, right? They will be delayed. They will be pushed up until you have the final exam. That does not make it too much difference, but at least I don't want to give you a little bit of a panic mode because midterm exam is only what 2 to 3 weeks away right now. Yes, so okay, and so so today what we are going to cover is the chapter 2, which is about the chemistry of life. The title is that, as the title said, the chemistry of life. To reiterate that, to remind you that life is nothing but chemistry. All these materials. We may consider our lives are so special, but if you really, really think about it, it's just a whole bunch of collection of chemicals. So then, if that is the case, then what kind of chemicals are there? And another thing is that the thing that I emphasize is that whatever the organic macromolecules, what are they? Huh? And how did you get there? Like, in order to build such organic macromolecule, what did you do? That's the basic concept or objectives of this whole chapter. But the dilemma, this is a kind of a dilemma for me, is that this whole thing is about boring chemistry. But this is just a fundamental essential for any science majors. Although science major, including engineering, they have a basic education already, experience in this part, the content. They are supposed to know basically what the carbohydrates are, what the proteins are, all those basic chemistry. But here in our classroom, they are not the only students taking these courses, but also students from various backgrounds, including all those my beloved Munhwa students, and so that's actually problem because to them this whole thing is just a whole news. I mean, they have never heard of anything like this. Probably the chances are. So then for them it is a kind of shock. What do I have to do? Do I have to know all of this? So that's because in order for us to get into the real subject of, for example, if we want to investigate the inside of a cell. What kind of cell structure we have and what are their functions that actually the main entree, for example, of our whole entire, that one of at least part of them. But then to do so, this is just one fundamental basics that we have to know, because we are going to talk about some of the structures inside of cell, and those structures are made of blah blah blah. And for example, this whole cell membrane is made of a phospholipids, bilayer, blah blah blah. And what are these phospholipids? And some type of at least we have to be aware of, or at least we have to be a little bit of a familiarity with these chemistry characteristics. So there's no way for me to skip this chapter, no matter how unpopular this chapter, the content is. And the good thing is, there are not much of things that I really have an intention to put them on the exam. Regardless, whether I just put some of this content on the exam to torture you or not, still, this whole thing is actually fundamentally the basic, so that we better at least know all this stuff to at least to put everybody on the same page. Okay. That's the kind of purpose of this chapter. So, like, for those who have already had this in your high school, as a biology major or engineering major or chemistry major, you must have all had this. Okay. Then take this opportunity as a kind of a review session, so that reinforcing your kind of knowledge. Well, do I really know this? Okay. Do I really understand this concept? And on the other hand, for those who have never taken anything like this, because you're like philosophy major or literature major, good, yeah. I admire you. I mean, no joking. I admire your major as like. Then this is for the first time that you observe, but you do not have to know everything. Of course not. Majority of things that we are going to cover is actually probably you will never have to worry about for the rest of your life. But at least, I heard some of them long time ago in that stupid class. That stupid guy mentioned some of the things. Then later on in your life, okay, that I know. And when, in reference to this, some of the more relevant life-related things, subject, pop up for the rest of your life, whenever that might happen, or it might never happen, depends on what kind of life you have. But then at least you heard, and at least you heard some, still vaguely remember some of the fundamental principle of the chemistry might be just good enough. Okay. So just because you cannot understand any of those things that I throw at you today doesn't mean that you are just failing, at least understanding this chapter, because it's just for the first time. If that was the case, yeah. And it will take some time. For everybody, it will take some time to get used to it's some of the untested water. Yeah. So at least try to get as much as you can. Don't panic. Okay. It's just kind of my 2 cents for those who non-science major who are taking this chapter. Okay. So having said that, let's go. So, okay. So life is chemistry. What is this? So whatever those complex things like complex hair molecules, that if you zoom in, basically fundamentally, it will end up what are made of all this really, really complex you're called hair is nothing but I gotta do really something about this. I cannot really stand this. This basic atom. So everything constituting life actually is made of fundamentally very small chemicals. That's what life is chemistry. So it states the ultimate goal as I went over briefly. So our whole agenda is this macromolecule, organic macromolecule. But in order to understand what kind of macromolecules are there and what are their functions, then inevitably we have to understand some of the basic components from which the basic macromolecules were built. That's the whole idea. Nothing else. So to show you, really show me what kind of macromolecules are there, is just one example of, I took this figure from one rather upper level cell biology textbook of one kind. By the way, this is not our own animal cell, but it's an example, typical plant cell having very rigid outside boundary called the cell wall, which we don't have. But other than that, almost everything else is basically same as our cells. So if you actually, by the way, we have to worry about memorizing any of this, but simply just recognizing. Yeah, that's the idea. Recognizing, there are a whole bunch of some very important, structurally speaking, structurally and also functionally, component inside of our cells, including, for example, like cell wall, which only the plants have. But cell wall is basically made of something called the carbohydrate. Everyone at least heard about what carbohydrates are. Okay? Even though we don't know exactly what are they, but we have heard carbohydrates. Yeah, that's the type of macromolecule that we are going to study through this chapter. And on the other hand, for example, outside the boundary cell membrane, there are lipids. Cell membrane is basically built by lipid. That is another kind of macromolecule. But not only that, also some proteins are also embedded on the cell membrane. Lots of proteins are there. So protein is another such macromolecule. So there are so many different structural and functional components inside of the cell that we are going to also take a look at in the following chapter. But also, if you look into the nucleus, inside of nucleus, and there is a DNA. Where are you? Okay, there. Here, the DNA. Actually, if you didn't know that the DNA that we knew, we thought we knew, actually not only the genetic material, the chromosome, the vehicle carrying our genetic material, the DNA, is not naked DNA, but also covered with heavily covered with this protein. Okay, I will stop here. Basically, whole idea is whole life is just made of a whole bunch of different types of many different kinds of macromolecules, right? But one good point is here, this macromolecules, organic macromolecules, how did you build this macromolecule? You start from very small basic fundamental unit called atom, but then several atoms combined together to build molecules. So that's the difference. atom, molecules, and finally macromolecules are something much, much, much larger, bigger, heavy molecules. And then probably some of you may actually have a question that, okay, then how did you end up? Let's say, okay, from atom to molecules, and also from molecules to macromolecule. How did you build this? What kind of specific way to build this? That's another thing that we are going to study, because that is important. Okay, so that's the whole idea. And another thing is, even though it looks so sophisticated, but at least the bottom line is, speaking of our ultimate goal of macromolecules, there are only 4 kinds, which is good. There are only 4 kinds of macromolecules. Can you name? We all know already. We have also mentioned over here. There are only 4 kinds of macromolecules. Wherever you look for, present in any living things, there are only 4 kinds of macromolecule, which are, one is carbohydrate, another one is protein, good, lipids, and finally nucleic acid, right? Of course, protein, under the head of this title of protein, there are tens of thousands of different kinds of proteins exist, of course. And lipids, how many different lipids are there? Of course. And carbohydrates, so many different carbohydrates. But who cares? We don't have to worry about all kinds of different things that they try to memorize, but simply, instead, what we are going to do is, what is the distinctive characteristics of carbohydrates? So that walking the street, if we run into somebody and who are you? Are you carbohydrate? Then she said, no, I'm not. Then show me kind of the criteria by which we can determine whether, if this thing was a carbohydrate, then it's got to be something like a characteristic. Same thing is in the case of a lipid. Okay, if we are going to call this guy as a lipid, then it must possess some of a fundamental feature, characteristic. That's all we need, actually. That's something important. And if for protein, if this was protein, of course I'm lying, this is not a protein, but then it must carry some fundamental, specific, distinct characteristics, chemically characteristics, making this as like deserving to be protein. Same thing. And better thing about nucleic acid is, unlike the other 3 kinds of macromolecule, in the case of nucleic acid, luckily, thank God, there are only 2 kinds of nucleic acid. That's good. Which are DNA and RNA. Right, good. So even we don't have to worry about memorizing all different kind of nucleic acid in the case of nucleic acid. That's it. So all these atoms. Atoms are basically sharing some fundamental basic structural organization scheme. With that, there are several different, many different kinds of atoms that we call each different atom as an element, like hydrogen, and this carbon, everyone knows this carbon, and oxygen, fluorine, and helium, and all this symbol. Chemists love using symbols to designate different elements, and there is a specific reason why they were aligned in this specific rows and columns that we happen to call this as a periodic table. And if you were a poor science major, probably in your high school, you may have to be forced to memorize even all this periodic table at one point of your life, which was very stupid, to say the least. But anyway, we are not going to do any such thing, such nonsense in this classroom. It is just showing why I am trying to show this to scare you, simply to show that there are so many different elements. Okay. And another point is, out of these so many different elements, luckily, not all of these elements are actually participating equally in building of life, but luckily, only some of them, very few of them, for example, to name a few, hydrogen and carbon, and some very few of them are actually abundant as a major constituent in the life for some reason. And for just the rest of this whole bizarre element, unless you are unlucky chemistry major or chemical engineering major, we don't have to worry about. That is another good thing about this studying life. So, atom. This is the basic structure of an atom. Different element, should I say. Different element has a different kind of different numbers of all these components as an atom, but regardless, all different elements share basic this organizational scheme in that at the center. So this is something different from the nucleus of the cell, which is obviously, but we also call this as a central part as a nucleus of an atom. And this nucleus of atom is made up of two different kinds of particle. One is called proton, which takes a positive electrical charge, proton, and the gray thing represents neutron, which is electrically neutral. Okay, and at the perimeter outside, very tiny bit of little cutie particle visibly moving around, which is, what is this? Electrons. And electrons, by the way, takes negative electric charge. So any given standard atom or element electrically neutral, because it cancels protons and electrons, their electric charges cancels each other, make zero. Okay, electrics in charge wise. In other words, that means usually any given element, the number of proton and the number of electrons should be what? Equal, the same. That's it. That's easy, right? And just like we have a weight, this particular element also have their unique characteristic weight. Okay, we call that an atomic weight, or when they build the molecule, then we call that as a molecular weight. Their intrinsic unique weight. How heavy are you? That is determined by, guess what? Only this central part. Proton and neutrons. Because, why? Why do we ignore? Why do we ignore this little cutie electrons? Because they are too little cutie. Just like, oh, by the way, I forgot mentioning. Today the weather is too good. Yeah. The weather outside is too good. It's just like this electron is too cutie and too little. Anyway, so practically, realistically, this the weight contributed from electrons can be easily, safely, and legitimately ignored. So only the weight we worry about this central part, the protons and the neutrons. Okay, that's it. Why am I mentioning this? Because no matter how much I hate having to mention this so-called isotope, that the position, the significance of this isotope in biology is rather like high. So I have to mention some, at least part of this, the isotope. What are isotopes? By definition, these isotopes are same elements that I showed on the periodic table. Like, as I mentioned, each given element will have a characteristic number of electrons and protons, right? But on some occasions, they behave similarly. For example, there are C, so they are all carbon. But what are these numbered? The superscript number usually we designate as indicate their atomic weight. In other words, their weights are different. Their weights are different. Oh, what is going on over here? So this illustrates very well of the concept or definition of this isotope. So can anyone define isotope? So these three kinds of carbons are all different carbon isotope. Okay. So then what are isotopes? Exactly. Thank you. What's your major? There you go. So you're not going to get anything. Sorry, but thank you. Exactly. So, like their protons and electron numbers are identical, of course, as a carbon. That actually defines the identity of any given element. But weirdly enough, the number of protons are a little bit different in that this something called the C13 has one more extra neutron, and the C14 has two more even neutron. So as I said, neutron and protons will provide some impact in weighing the weight, right? Atomic weight. So that's why their mass, their weight, their masses are different, even though they are all the same carbon. Why do you have to worry about this thing? Okay, fine, good for them. So they have diversity. Always they have diversity, which is better than just not having it. Good for you, good luck. But why do we have to worry about the isotope? Because some isotope is like we utilize very valuably utilize in the purpose of pursuing and making a progress of this life science. Especially something called, in the case of radioactive isotopes are the one that we utilize heavily in life science. Then we have to know first, then what's radioactive? So here, among these three different isotopes, two isotopes are non-radioactive, whereas the only C14 is radioactive. And also, as you can notice, the relative proportion C12 is a kind of a, so to speak, we can call as a standard carbon in that almost 99% of the entire carbon existing on Earth are actually C12. So basically, we can ignore the others. I mean, these are the vast majority. Why do you have to worry about the others? Simply ignore. Doesn't make any difference. True. But at least still it exists as a 1%. The C13 heavier, a little bit heavier than standard C12. And in the case of the C14, that is a radioactive. That is something that and another thing is, to tell you the truth, these three carbon isotopes are not the only carbon isotope. There are several more carbon isotopes, but why didn't they show up here? Because they can be just ignored. Look, this one is even less than 1.1%. So the other more minorities carbons are actually simply really tiny little bit of the amount exists in. So we do not really have to worry anything about those. So these three carbon isotopes are the one. In case we worry about carbon, then these are the only three that we have to concern. But anyway, this is only radioactive in the case of carbon. But then we have to know what exactly the radioactive is. This is something about the energy. Some isotopes are much higher in energy. So whenever they have a high energy, they become unstable. So they want to go back to, they want to change their identity into more stable one. That's a kind of a rule, basic golden rule of anything in whole universe. Anything unstable, because usually why are you unstable? Because I have too much energy. Then how can I become more stable? Hey, it's easy. Dump your energy. Huh? Stupid. Then you are so unstable. Why? I have so much money. Easy. Just throw your money to somebody. Then you will be more stable, so to speak, happier. Right? Just like that. Exactly. So these isotopes with high energy, so very unstable, so they just want to change their identity into more stable one. But the way they can achieve is emit. This dump their energy and then come back to a stable. Dump the energy as a decay. We call it as a radioactive decay. That is a little bit of a complex one, so we don't really have to worry about. The only thing that we need to remember is radioactive isotope will emit energy in the form of radioactivity. Radioactive. Okay. Several different types of radioactive energy is illustrated. Alpha, beta, and gamma basically are three major types of radioactive. And how do we prevent, how do we shield different kinds of radioactivity? So that's just kind of to show we don't have to worry anything about memorizing these things, but simply, high energy. So that's why we usually consider as a radioactivity as something dangerous. Why? Why do we want to avoid approaching, stand very close to nuclear power reactor or anything? Because it will emit such a huge amount of energy because they are basically radioactive material. So such a high energy will damage you. Like your DNA, your skin, and any high energy will destroy those things. That's why. And this figure illustrates the kind of time it takes for any given radioactive material to return to a non-radioactive thing we call as a half-life. Where are you? Half-life. To put simply what half-life is something like, in the case, for example, C14. What's the half-life of C14? Let's say we have 1 gram of C14 initially, radioactive. And if half of this 1 gram of C14, in other words, 0.5 gram of this C14 now become non-radioactive something different things, okay, usually C14 will become nitrogen, okay, through this decay procedure. And how long will it take if until this entire thing, half of this entire thing, original entire thing, will become non-radioactive? In other words, another half, another 0.5 gram of C14 still remain at that point. That's the half-life. That's the definition of half-life. Obviously, different type of radioactive isotope, like different type of element of a radioactive isotope, will have their characteristically different half-life. In the case of carbon, it will have something like a 5,000 years. It will take 5,000 something years until half of this thing will become non-radioactive. So that is the reason why in this country, Korea, in the academic laboratories, using this C14 as their tools, a diagnostic tool in the experiment is not granted. We cannot. Think about it. If you mess up something, if you made a mistake, so if you spill this C14 on the desk, laboratory bench, then you cannot do anything. It will still there until half of them become non-radioactive. It will take 5,600 years or something. It will take grossly long years. So it's a very sensitive matter. So regulation. But hey, can't you use something else? Why do you really have to use the C14? Kind of. But the country where I was studying, the United States, C14 was freely available in the laboratory, so I was able to use the C14 in my experiment. But whenever I had to touch this C14, I was kind of a little nervous because I know if I do something stupid, then it will take 5,000 years. Okay, so I better not. But in reality, actually, C14 is nothing. Even you can drink. Nothing will happen, actually. It's very weak in its strength. So you don't really worry about this. But still, kind of precautionary measurement regulation. On the other hand, another isotope like phosphorus, P32 is a very famous radioactive isotope. That one is very strong, relatively. Okay. That was my favorite choice of the experiment when I was using in my graduate school. So every Friday I had this little moment after hours, turning music so loud in the laboratory and then just like dancing around and did the experiment with this P32 because nobody's around, so no one is going to. And this thing, I actually was much less nervous because why? Guess what? The half-life of this P32 is only 2 weeks. So even if you just do something very stupid, that, hey, just give him 1 month, it will all go away. After 1 month, everything is always like undercover. So you can just put them in the regular trash and zip your mouth and nothing happened. So that's the difference. That's just kind of a difference in the half-life of different isotope, okay? Why I'm actually trying to put so much emphasis on the half-life, because it matters that what we are going to introduce the concept of these things. Anyway, so boom. So what two major in the regular laboratory, two major usage of this radioactive isotope is one is diagnostics. Okay. Detect something. Of course, analysis, especially in this category of diagnostics, usually in the medical laboratory, it's been a very important and vital part of their research, and also the taking care of the patient. What do I mean by that? This, for example, how do you know whether a patient throat cancer is growing. Usually, if you want to detect some of the suspicious things developing, you try to put some PET scan or CT scan, or in some cases MRI, and all those diagnostic imaging is rely on, to some degree, rely on radioactive materials. For example, you can put some of the radioactive C14, for example, in, let's say, glucose. Oh. I was going to write glucose in Korean. I just thought. Glucose, glucose is basically carbohydrate. It contains several carbon. But then it is possible to put some C14 incorporated into glucose. We call that as what? Labeling. We label some particular object with the radioactive isotope. Why? Then we can do this. It is possible. Detection. This radioactive isotope emits energy. That energy can be detected by some specific instrument. So, what the basic whole idea of this thing, why anything lit up by radioactive C14, that means glucose is going over there, okay, for example. Why do we have to worry about glucose is going into specifically on this particular area? Then we try to connect this thing as a kind of a potential cancer, because glucose is what? The energy source. Whenever you need energy, glucose will just go there, because we are going to break the glucose down and then get the energy. Unusually heavy traffic, just like on a bank system, whenever there is some kind of very unusual traffic of money is coming in and coming out, then we suspect something is cooking. So is in our body system. Unusually heavy amount of glucose is being collected over here. Why? That means this area is demanding unusually high amount of energy. What's up? What's up? Because this cancer is growing. Cancer always require much higher energy and take some energy from others. That's why we call that as a cancerous, and try to destroy them. That's basically the very good usage of this radioactive isotope after labeling some of the target molecule, for example, glucose. There is a way, technically, it is possible that we put C14 radioactive together with some regular standard C12. Whenever there is some incorporation of a radioactive material in our target molecule, we can follow, we can trace, that's a vocabulary, we can trace whenever those radioactive isotope goes. Actually, in the case of MRI, when you try to take the MRI on the brain, for example, you follow the oxygen. In the brain, whenever there is an activity, the brain will demand a high amount of oxygen. Why? Because mitochondria, in order to produce ATP, they will require the oxygen. So whenever there is a high oxygen goes, that means that part of brain is very active. That's the basic principle of having this MRI scan of brain, for example. So same thing. Similarly, radioactive isotope can also provide such opportunity for us to detect. So like this whole cancer is growing, we can detect live on this image. When you Google, actually this, I took this image from Google, the Wikipedia, I guess. So that's the indication and clue for such thing. Another very major area of this usage, especially carbon, is something called radioactive dating. Don't think anything like a romantic dating. No, it is not. Carbon, for example, carbon dating or anything like a dating, using the radioactive material, we are estimating how old this sample has been. Okay. The age of the sample can be determined by using this radioactive. In that case, we are calculating this half-life. So it depends on the half-life of the particular. So especially these two particular radioactive isotopes, one is a carbon C14, and uranium is also very notorious high energy radioactive isotope. So using carbon, you can estimate the age of the particular sample up to, accurately you mean, up to 60,000 years. Of course, you can also estimate age approximately how old this sample has been, even beyond the 60,000 years, something 100 or 200,000 years. But the accuracy will be compromised in that case. But in the case of this uranium, even you can estimate 4 billion years accurately. That means you can estimate how old this particular rock has been around over here. Kind of thing can be possible using this thing. But what's the rationale? What's the rationale behind this estimating the age of this particular sample using this radioactive isotope? To give you a clue, if you can answer to this question, then probably that you understand the principle of this radioactive dating. So, would you give it a try? The question was, this carbon dating can be also applied to a live object. That means it's like it's a kind of a hidden message of it cannot be. This dating, radioactive dating, can only be applied to a dead object, non-living, or the living object, but once lived object, no longer alive object, can only be subjected to this radioactive dating. That is true, actually. You cannot use any live object. Object is all weird, but life form, a living thing, cannot be subjected to this radioactive dating. Why? Why is that so? Is it too dangerous? Oh, no, that shouldn't be a reason, right? Well, yes. That's a P32. That's good. The carbons, they half-life is a 5,000 something, like 600 years half-life. But just because that doesn't mean that, fine, the half-life, the first half-life might be this particular 5,700 at least. Okay, so at this year position, the original half 100 will be reduced. The radioactivity will be 50, but on this time point, even if not 5,000 years, but something like 100 years, still there is some kind of a meaningful calculation can be made. Yeah, that's no problem. or even go all the way down to further in the past, still you can apply this whole thing because you can extrapolate, right, the thing. So that is not an issue, but only it may slightly affect some accuracy beyond this point, obviously. But other than that, yes. So with that, why cannot use this whole principle onto any living thing? So basically what it means is this whole thing about radioactive dating, including carbon dating, is something like indication of how long ago this particular object was dead. That's it, right? That's the kind of information we can get out of this dating. Of course, it will be very, very valuable information. Like, for example, you just scavenge the fossil. You wonder how old this fossil was. Like, it could be 5,000 years old fossil, or maybe 500,000 years old fossil. Who knows? Okay, or even 5 years old fossil. Your chicken bone. It could be a chicken bone versus a dinosaur bone. Who knows? How do you know? Then, in that case, this carbon dating will point out accurately whether you're wrong, in the right track or wrong track. But the problem is, why can't we do this in the living object? Why? Because living, yes. In this case, I have to give you some extra incentive. Your name, lady, please? This? Am I right? Okay. So you will have, wow, +2 on your in the final exam, whole together, okay? Congratulations. Yeah, that's exactly right. The living thing will constantly have this circulation from within and with the outside of the whole environment. So carbon will also circulate. So whether it is a C14, C12, C13 will just all come into your system, and then it will escape eventually out of your system. But once you're dead, whole thing just suddenly, all of a sudden, the door is shut. What happened? Let's say C14 accidentally was imported as part of your lunch. Well, yeah, it exists as by less than 0.1%. There is a C14, like let's say you ate pap or bang or whatever, but still there are very small portion of this carbon making up is actually the radioactive C14. Yeah. When you're alive, it doesn't matter because it will go away eventually. But once you are dead, hold this circulatory circuit door has been shut off. Now it will remain inside your body. Then what happened? It cannot get out of. It cannot escape. Then what happened? Now, that poor C14 trapped in your body, your dead body, will now start what? From then on, it will start this decay. When you are alive, this decaying cannot be measured because it will go away. Okay. But now this particular C14, whatever the amount, was trapped inside of your body, now cannot go anywhere else, and then it will start decaying. So let's say 5,000 years after, your body was, fortunately or unfortunately, was discovered. And then the people who found your body wondered how old this body might have been. So this is one very reliable way of measuring those things. Let's take a sample, and then let's try to analyze how much of C14 is there. Okay. If that was freshly dead material, your body, sorry to say so, but then it will be something like that C14, the proportion-wise, will be something like less than 0.1%. But after 5,000 years, probably it will be half of that 0.1% something. Then you wondered, oh, this C14 was supposed to be in this as an amount of something like less than 0.1%, but why is it only half the amount of what is supposed to be there? That means it took half-life. One half-life was over something like 5,000 years. This poor body has been dead and here buried around for 5,000 years. You can expand this idea. So that's how you do this carbon dating or any other radioactive isotope dating. Okay, so the next task is, this isotope is actually small potato. Our actual real agenda is, before we go any further, no. Our next agenda is to have major, in biology, the major different types of chemical bonds. Okay. So these chemical bonds are the one with which different atoms get together to form a molecule. And also different molecules get together to form what? Macromolecules. So that's the chemical bonds. So it's just like, so to speak, chemical bonds behave like the glue, molecular glue, with which we can attach some of the objects that we want to put together. But unfortunately, there are only the single type of chemical bonds, but there are several different types of chemical bonds, especially even with that, inside of life, still there are several different types of chemical bonds are actively engaged in maintaining the life. So that's why we need to at least make a list up of major, important, biologically important chemical bonds. Why? Because they are the one who make, for one, some of them is the one actually responsible for building these macromolecules. So we need to know that. And also other types are, they may not be directly involved in the building macromolecules, but once those macromolecules are formed, then these other types of chemical bonds are actually playing very important role in making their specific interactions together. That's more important thing. So, having said that, one such chemical bond is called ionic bond. Just like we have different types of glues, there are several different types of chemical bonds available here. Another thing is covalent bond. And another type is hydrogen bond. Probably these three types of chemical bond, a lot of you must have heard these names at least before. And maybe let's try this. How about this? Van der Waals. What is this? Van der Waals bond or chemical interaction. Have you heard of this? Van der Waals? You should. And finally, hydrophobic. This is not actually bond. We only call this hydrophobic as an interaction. But let me explain why this one is not called bond, but something rather interaction. But anyway, at least these 5 different types of chemical bond or interactions are the one actually you will be encountered. You will be encountered when you study the macromolecules function, because they are the one actually influence their functions. And also, when you also go further in the cellular structure, they are also the one that actually will also haunt you again. You didn't know this, kind of. So here at this point, at least we are going to make sure that, okay, these are the different types, and what are their differences, characteristics, and how they are used, the type of, at least those 3. By the way, all these are summarized in your lecture handout. Okay. I'm just giving you one enough advance warning about this is our first goal to recognize the differences, and also how they are used. Those are 2 objectives. That's all we need actually know about this. Nothing else. By the way, to give you one bottom line first, there's something called covalent bond. The names maybe weird enough. This is the one actually responsible for generating, building all these macromolecules. Regardless, 4 different types of macromolecules: protein, carbohydrate, lipids, and nucleic acid. Okay, they are all use this one particular type of covalent bond we call the covalent bond to become heavy macromolecule. Why? There's got to be some reason. Why? Because this is the only chemical bond which is strong enough. Strong, in other words, first, characteristically speaking, strong. Covalent bond is strong and reliable. Long-lasting, in other words. These 2 characteristics are actually ideal for building macromolecule. If not, for example, if this is weak, or if this is unreliable, then let's say you build starch, huge starch molecule. Then if that chemical bond generating this starch molecule, to give you the answer, starch molecule was made of whole individual glucose molecules, but anyway. Then if this one is not strong enough or unreliable, then it will break so easily apart. Okay? Then how can you rely on the starch as your energy storage? If cell membrane, which is made by lipids, one specific type of lipid, was not built by covalent bond so that it is not strong enough or not reliable, then your cell membrane structure is unreliable. You never know when it will simply break away and then it disappears. That's the issue. Okay. So one particular reason, this is the only such strong and reliable, long-lasting chemical bond. So there is no choice but simply to use this covalent bond as a building for the platform for macromolecule building. Others, then what are they? They are, so because of that, others, something like ionic, hydrogen, van der Waals, hydrophobic, whatever, they are all collectively called non-covalent bond. So there are something, the world of chemical bond, one group, covalent bond, and the rest of things is simply called the non-covalent bond. Why? Why can you simply put everybody else as a one category as non-covalent bond? They have a similarity of being weak, unreliable. So all others are very weak bond, comparatively speaking, relatively compared with covalent bond. Still, why do we still keep them? So ionic hydrogen, van der Waals, especially this ionic bond too. All these non-covalent bonds are nonetheless extremely important in maintaining lives. Actually, this weak and unreliability is actually the point of attraction. So we are using this to make some of the, for example, enzyme. Let's say enzyme always requires some specific substrate having an interaction. If this interaction was too strong, like covalent, so that based on a covalent bond, as an enzyme, this guy's functionality is simply useless. Why? Because for enzyme, speed matters. So you have to quickly put your target and then quickly get it done and then dump, say farewell, and then try to find another victim. That's what one particular enzyme makes very efficient. If any enzyme is so stubborn, reliable, so that having this interaction with the substrate through covalent bond, then it is very strong, reliable bond. So once they are formed, it will not be broken. It's never be broken, but it will be very difficult for them to break. So in other words, it will take forever for this particular enzyme to finish one job. As an enzyme, that's just garbage. So we do have such many occasions, examples of such activities that require very quick, flexible interaction. For that, all these bonds, other than covalent bond, ionic, hydrogen, van der Waals, hydrophobics are the one actually very ideal and suitable. That's why in biology they are acting was a very important roles here. I think I forgot something. Another thing is, because this covalent bond is very strong, that's why organic macromolecule, not all but some, at least some organic macromolecules can also serve as food. That's another important reason. Why? Because all these organic macromolecules were built using covalent bond. This covalent bond is strong. What do you mean strong? In other words, it's very difficult to form. Strong bond is difficult to build. It's expensive, right? And also strong bond is very difficult to break it. Expense can be compared to what? Energy. Okay. So it takes energy. So any subject or object, any object built through covalent bond contains high energy because of this chemical bond. So glucose, so no wonder why glucose is built through covalent bond exclusively. Carbon's connection was basically built through covalent bond. So in that way, each covalent bond contains high energy. So when you break each covalent bond, of glucose, you get high amount of energy. That's what make glucose as good food. Okay? So far, what do you think? Is it still like okay for you to follow, or is it okay? So, this is something I don't really want to go into too much detail, but just a basic elementary chemistry of the basic principle behind the of chemical bond. Why different elements form chemical bond to begin with? Because of the electrons. Simply put, for the rest of the more detailed thing, you may want to go through on your own on the lecture handout. But in order to save some time, let me simply go through like this. Different elements have a different layers of electron layer, sort of thing. We call this electron orbit. Yeah. So smaller element like a helium. Helium is very small element relatively. It's just slightly larger than the smallest element, which is hydrogen. So helium has two electrons and one layer of such orbit. But as an element gets bigger and bigger, you get to expand the layers of electrons, the electron orbit. Why? Why do we have to? Do you notice something with you looking this diagram of electron orbit? Why do we have a different electron orbit among different elements? What's the understatement of this? Why can you, like, just because argon doesn't mean that, why can you have all these electrons have one layer of electron orbit? Maybe they are crowded, but still, what's wrong? That's the limitation. There is only certain amount of electron can be put in a given particular electron orbit. So as an element, as you grow bigger and bigger, you have to accommodate more layers of electrons because each electron orbit can put up only so many. Okay, there is a kind of maximum limit for a given electron orbit. Having said that, that's not important. You can forget about that. The issue is the most important thing is the outermost boundary, the outermost electron orbit. That's the number of electrons occupying the outermost electron orbit is the one actually shaping or determining the chemical nature of any given element. And another thing, important thing is, important or maybe not important, this, for any elements that we have to worry about in biology, luckily, the maximum amount of electrons at the outermost electron orbit is only, guess what? 8. 8 is the maximum. In the case of this argon, how many? Let's count. 1, 2, 3, 4, 5, 6, 7, 8. Right. And neon, 1, 2, 3, 4, 5, 6, 8. This 8 is maximum, and once you can fulfill this 8 maximum number, then for an element, you have just reached your ultimate goal. So everybody, as an element, everyone wants to reach this goal of whatever, this ultimate goal of achieving the maximum amount of electrons at the outermost electron shell. Why? Because by doing so, you can become very, very stable, unreactive. So you don't have to worry about anything, any stupid chemical reaction anymore once you achieve. So everybody wants to follow, I want to be just like neon or argon. Here, by the way, these three are such an exemplary element, all of which they have achieved such goal of reaching the maximum electron at their outermost electron shell or electron orbit. In the case of helium, the maximum electron is only 2 because it has only 1 electron orbit. But for these, the other two, the maximum electrons are 8, and they have fulfilled. They have accomplished obtaining the 8 maximum number of electrons, and all these are unreactive because of that. I'm done. I'm finished. I got degree and graduated. All this thing. Yeah. Everybody else who hasn't achieved their maximum number of electrons, just like for many examples, only 8. They just want to keep trying to reach that goal, whatever it takes. And that is the reason why they are engaged in chemical bond. So, yeah, I cannot go further than this. So let's take 25 minutes and then let me continue on. So I don't want to go into this. It is unpopular things, but in order to explain why such chemical bonds are to begin with necessary, I have to explain this, whatever the stupid maximum electrons at the outermost or whatever thing is. Actually, that's the reality. That's the truth. So that's the reason why I have this. And then with that, see you in 25 minutes. And during the break, like I said, once again, I'm going to go over some of your student questions. And another thing is, I'm basically a very, very lazy, lousy guy, as you know by now. So once I have to collect the scrap paper of attendance, I don't really reflect this whole thing, record on the official the attendance site yet. Okay, but I'm still keeping the record. So in the meantime, you may notice that, hey, I was here, but it was recorded as an absent. Don't you worry. Yeah, well, I will take care of and make everything all right after all eventually. So in the meantime, some of those records will not be reflected in real time. So that's once again my apologies, but I will try to do these things later on. Okay, so